This is 40 Days of Chemistry, part 24, this time looking at 9.4.5 water. And one of the first things you need to understand is what water quality is. Now, water quality depends on if you're talking about drinking water or environmental water. So water quality is commonly defined by its physical, chemical, and biological and aesthetic appearance and smell characteristics. And healthy environmental water is where it supports a rich and varied community of organisms and protects public health. That's like a general blurb about water quality. The Australian Drinking Water Guidelines have some very specific details though. They're on the page just there. You can see that for every particular thing we looked at, TDS, lead, hardness, turbidity, BOD, bacteria, etc., there are some guidelines of what good water or clean water has to have. So moving on, what we're going to look at is first of all the treatment steps. Then we're going to look at all the pollutants, their sources, treatments, and what we can do about them. So water treatment generally follows the same basic sort of steps. First of all, we have screening, which is to remove large objects. You've got aeration, which raises DO, and also oxidizes some ions, such as iron and magnesium, to make them become precipitates, which then can be sedimented or filtered out. You've got flocculation, which is adding chemicals like iron chloride or iron 3 chloride, or alum, which is aluminium sulfate, and that helps fine particles to coagulate so they can be sedimented and filtered. You've got the sedimentation step next, which is where coagulated particles sediment out into a tank for removal. You've got filtering, where fine particles are removed by a filter, usually a sand filter, or at this stage you could also use membrane filtration, which we'll look at in just a minute. Then you've got disinfection. You add chlorine gas, which is pumped in at high pressure to kill microbes or microorganisms. You've got stabilization. You add sodium carbonate, which raises the pH to 6.5 to 8.5, which is ideal, and that's because the iron 3 chloride and alum you add to flocculate or coagulate sometimes lower the pH. In addition, adding sodium carbonate helps to remove calcium and magnesium ions, which can help to decrease the hardness or soften the water. And finally, you've got fluoridation, adding fluoride ions, which helps with dental problems, but it's not needed for actual purification of the water. So what's a membrane filter? A membrane filter is a synthetic polymer membrane or synthetic polymer sheet with very fine and very precise pore size. 100 nanometers for microfiltration down to 0.1 nanometers for reverse osmosis. And it removes all particles that are bigger than the pore size. And that means because these pores are so small, it can remove bacteria, organic molecules, and even ions in reverse osmosis in desalination. Now you have water flowing parallel to the membrane at high pressure, which means the water passes through, but the particles do not, and it doesn't cause the particles to clog the pores because the particles are moving parallel to the pores rather than pushing into the pores. This can't be used for primary water processing, so you need to do some sort of sedimentation or some basic filtering first, and it can't be used for raw sewage, otherwise the pores will be clogged too quickly. The good thing about membrane filtration is it avoids the need for chemical disinfection because it actually removes microbes. It's also, the polymers are quite tough, and you can use high pressures, therefore the flow rates are quite fast, therefore you can purify a lot of water. Now some of these pictures just show you a few details about membrane filters. So you've got the membrane filter here, okay, which looks like this funny tube. The clean water will end up going inside here, so the dirty water is pushed in to this like foamy looking bit here, and the clean water then permeates through the filters into this middle core. Now each one of these little tiny tubes inside here looks like this, and you can see that it's got a very thin wall and there's pores inside. Looking at the surface, you see these tiny little pores, precisely sized pores on the surface, which allow the water to flow through. And here we've got the water flow is actually going across or parallel to the filter at high pressure. The water permeates through and the solid particles, the unwanted concentrate, keeps flowing past without clogging the pores. Looks like the first pollutant we look at. The first pollutant we look at is common ions. Now common ions include any common ions such as sodium, potassium, chloride. Sources of them are runoff from farms, runoff from mines, runoff from industry and urban areas. Over irrigation in farmland causes dryland salinity, which then flushes into the waterways as well. How do you measure common ions? You can use AAS. AAS can be used for some specific metal cations, and that's a quantitative measurement, or you can use precipitation testing or gravimetric precipitation testing, which is qualitative or quantitative. TDS is an important measurement mentioned in the syllabus of ions. TDS is a measure of the total dissolved solids, i.e. salts or ions, and it's measured in parts per million ions. You can determine it by a probe, which is a conductivity probe, or you can weigh and evaporate a filtrate, and that will tell you the TDS as well. How do you treat for common ions? Some you can oxidize by spraying or aeration. Some you can flocculate out and precipitate out. You can use membrane filtration though to remove some common ions as well, for example desalination. Now pH is one we need to look at. Now pH is caused by ions, pH is caused by hydrogen ions or hydroxide ions, and this is an easy one to choose. If you're going to talk about a pollutant and how you treat it, pH is really going to choose because the sources are quite simple. If you've got acidic conditions or low pH, it's caused by excessive hydrogen ions, and that can come from mining runoff. If you've got high pH, that's from too many hydroxide ions, which could come from industrial discharge. So it's an easy source. How do you measure it? Nice and easy. You measure pH with a pH probe or indicators. And how do you treat it? You treat it with neutralization. That's a really easy problem to talk about. So if I was going to talk about the problem, I'd probably go for pH. Hardness and turbidity come next. Now, hardness is caused by the presence of calcium ions and magnesium ions. They prevent soap from lathering, therefore stop the soap cleaning properly. It also causes scale on pipes and kettles and things. The source of calcium and magnesium ions, it could come from local geology. For example, if you've got limestone in the area, that'll make some extra calcium ions in the water, or it could be from mining activity releasing these ions into the waterways. How do you measure hardness? There's a qualitative way where you put the water in a test tube with some detergent, then you shake it up and measure how much lather there is. That's qualitative. Or quantitative, like we did, you can use the volumetric titration with EDTA and a Kalmagai indicator. You assume all the ions are calcium ions, and you figure out the hardness in parts per million calcium carbonate equivalent. So you figure out how many calcium ions there are, or you figure out how many calcium plus magnesium ions there are. You pretend they're all calcium. You then figure out how much calcium carbonate there'd be in the water in parts per million, and that's the hardness. How do you treat hardness? You can use water softeners such as sodium carbonate, which precipitate out the magnesium and calcium ions, and there are some things called ion exchange filters, which can remove calcium and magnesium ions. Turbidity is the next pollutant, and turbidity is another easy one. We talked about pH being a good one to choose. Turbidity is another easy one to choose. Turbidity results from the presence of suspended solids, which block light from the water, which is bad for things like photosynthesis. It's also bad for drinking water because it makes it look unattractive. The source of turbidity, nice and easy. Any runoff or erosion will cause turbidity. That could come from cleared land, such as farming or logging or industry, and runoff from urban areas. It can also be caused by algal blooms because the algae itself blocks light. So that's a nice, easy one to talk about. How do you measure it? You measure it with a turbidity tube or Secchi disc. You basically fill the water up to a certain depth or put the disc into a certain depth till you can't see the marks anymore, and that the depth of water is converted to NTU or nephelometric turbidity units. You can use colorimetry to measure it, or you can use a nephelometer, which is quantitative and less subjective than the use of the turbidity tube. How do you treat turbidity? Once again, a nice easy one to talk about. You can flocculate the particles, you can sediment them and filter them. So that's why I choose turbidity. pH and turbidity are very good ones to choose because it's easy to talk about the source, the measurement and the treatment. Next comes DO, BOD, nitrogen, phosphorus and eutrophication. DO is dissolved oxygen concentration in parts per million, and you measure that with a probe. Low DO can be a sign of thermal pollution from industrial cooling water. We know that high temperatures drop dissolved oxygen concentrations. Or eutrophication. How do you treat DO? You can use aeration. BOD is the oxygen used by microorganisms to decompose organic matter in the water over a 5-day period, and it's measured in parts per million, and it's BOD equals dissolved oxygen on day 0, take away the dissolved oxygen on day 5. You have the sample in the dark for those 5 days to stop photosynthesis occurring. And it's also, just be aware, you need to measure dissolved oxygen, therefore, to determine BOD. So there's a link between DO and BOD. High BOD water usually comes from sewage or agricultural waste, where there's lots of organic matter in the water, and therefore there's lots of BOD because the bacteria can eat those organic matters. High BOD is also a sign you might have bacterial contamination, and that's another one that's easy to talk about to treat. Bacterial contamination could come from sewage, it could come from agricultural waste. How do you measure it? You measure it with BOD or do E. coli tests. How do you treat it? You treat it with chlorine to kill the bacteria. So this is a nice, easy one to talk about as well. Nitrogen and phosphorus are also pollutants that are linked to this whole system. Nitrogen and phosphorus usually come in the form of nitrate ions and phosphate ions. They're measured using colorimetry or volumetric titration techniques. They involve multiple reagents. I don't think you need to actually know them in detail, but you have to be aware that you can measure them through colorimetry and titrations. You might get high nitrogen and phosphorus from agricultural runoff, such as fertilizer and manure, or detergent runoff. You can also get it from sewage as well, which I should have put in here. And that all these problems are linked to eutrophication. And eutrophication, it's where you've got excessive nutrients. So the nitrogen to phosphorus ratio is less than 10 to 1. You've got more than 1 part per million nitrogen or more than 0.1 parts per million phosphorus. And that can stimulate growth of algae, which is called an algal bloom. And when the algae dies, the decomposition of the algae causes the DO to drop, and that causes anaerobic conditions, which can then cause toxic anaerobic bacteria to grow. So eutrophication usually has low dissolved oxygen, high BOD, and high nitrogen and phosphorus. How do you monitor eutrophication? If you monitor BOD and nitrogen and phosphorus, that can tell you the risk of eutrophication occurring in a certain waterway, but monitoring DO and BOD can tell you the extent of eutrophication once it's already started. The last thing we looked at in the water topic was heavy metal pollution. Now, lead pollution in waterways, it used to come from the atmosphere, mainly from leaded petrol fumes, but these days it mainly comes from lead processing industries, industrial discharge, and runoff from tips, e.g. runoff from lead in the car batteries, which is dissolved and then runoff into waterways. In drinking water, in the household, it's mainly from lead and solder used to join water pipes. On average, 10% of all total lead in humans, so the lead that's been picked up by humans, comes from their water. And in ecosystems, it bioaccumulates, which means over time, the lead in your body or the lead in the organism's body keeps increasing because it's not excreted out, and it also biomagnifies up the food web because as creatures eat other little creatures that have lead inside them, the lead content in their bodies increases as well. How do you test for lead? You can test with precipitate testing. For example, the most common precipitate test is at iodide ions, and you get a bright yellow lead iodide precipitate. But also, if you know you're testing for lead, AES is the most highly accurate way of testing for very low concentrations of lead. And the reason why you've got to test low concentrations is being a heavy metal, it's toxic in very low amounts. What do you do if there's lead in the water? How do you treat it? It's not the greatest thing to have lead in the water in the first place. If you want to get rid of lead though, you can precipitate it out. Carbonate ions, sulfide ions, all the lead ions, all the lead compounds of those chemicals are insoluble, so you can precipitate it out. Or you can just replace the solder in your pipes with something that doesn't contain lead. Why is that such a concern? Well, lead's a neurotoxin, which means it damages your nervous system. It also has an impact on the circulatory system, skeletal system, and reproductive systems as well. Lead has no useful role in the body, and there's no safe limit for lead in the body. And just some example milestones on lead, I suppose. IQ damage occurs at 0.1 parts per million. Infertility and kidney damage at 0.4 parts per million. You get seizures at 1 parts per million, and it's fatal at 1.5 parts per million. And that's the end of the water topic.